Hi dear students. So now we'll discuss molecular orbital structure of thiophene. You can see sir is already written. No, I'm rewriting because in the last class we have seen the molecular orbital structure of furan. Both have the same structure, same properties, almost their structural properties. That's why I'm just rewriting on the structure. The molecular orbital structure of furan. So I'm taking that and I'm just rewriting. Okay. So if you see the first molecular formula of thiophene is, if I just remove this oxygen and if I write sulfur, this is the molecular formula of sulfur. You know, sulfur and oxygen come under the same group. So oxygen is 8 and sulfur is 16. They both come under the same group and they have the same properties. That's why if I just replace the oxygen with sulfur, that is over, that is done for the thiophene. So if you study furan, we can easily write the molecular orbital structure of thiophene. So that's why I'm just rewriting in this case. So here for the carbon atom, as you already know, the atomic number of carbon is 6 and electronic configuration in ground state is 1s2, 2s2, 2p2, and in the excited state, one of the 2s orbital electron will shift to the 2p orbitals. So here and it is also undergoing same sp2 hybridizations. Here also both carbon and sulfur are sp2 hybridized. sp2 hybridized. So here these three sp2 hybridized orbitals of carbon with the unpaired electron, and there is an unhybridized p orbital, an unhybridized p orbital with unpaired electron. For sulfur atom, for sulfur atom, you know, the atomic number of sulfur is 16, and if you write the electronic configuration in ground state, that is 1s2, 2s2, 2p6, 3s2, 12, okay, 3p4, okay, and in the excited state, electronic configuration in excited state 1s2, 2s2, 2p6. There is no change in this case because all this 1s and 2s will become 2p. So 1 and 2 principal quantum numbers, they will become inner orbitals. They do not involve in hybridization here. So one of the 3s orbital electron will shift to the 3p orbital. So it is become 3s1, 3p5. In the case of furan, the oxygen was 2s1, 2p5. Here 3s1, 3p5 for sulfur. So these do not involve in hybridizations, inner orbitals. So I am writing for a 3s and 3p. Okay, there are 3 orbitals in p orbitals, so that is 3px, 3py, 3pz. Yeah, in case of 3s there is 1 electron. In case of 3p there are 5 electrons. You know, they do not obey Hund's rule. That's why the pairing is not according to the Hund's rule. So here this is also undergoing sp2 hybridization. So 3s, that is 3s orbital and 2 of the 3p orbitals undergoing hybridization, that is sp2 hybridization, and these 3 become 3 sp2 hybrid orbitals, and there is still one unhybridized p orbital, one unhybridized p orbital. As in the case of oxygen, sulfur, both have the same thing. So if I just replace the oxygen by sulfur, sulfur is also sp2 hybridized, and 3 sp2 hybrid orbitals are there, and among 2 sp2 hybrid orbitals with unpaired electron that are forming sigma bonds, and there is one sp2 hybrid orbital with pair of electron that do not involve in bond formation, that will be present as lone pair over the compound. So, and still it has an unhybridized p orbital with a pair of electron. This is the electronic status of thiophene, sulfur and carbon in the case of thiophene. So now if you see the formation of sigma bond, so if I just replace this oxygen by sulfur, it is over. Here also just oxygen by sulfur, it is over. So please just you can get it. So all carbon carbon bonds, carbon carbon sigma bonds are formed by sp2 overlapping, and carbon sulfur bonds are formed by sp2 overlapping, and each carbon are forming a bond with hydrogen, that is sigma bond. sp2s overlapping leads to the carbon hydrogen sigma bond, and there is a this one, this unhybridized p orbital with lone pair of electrons will be non-bonding pair of electrons that do not involve in the bond formation. So if you see its summary, carbon carbon sigma bonds and carbon sulfur sigma bonds, they are formed by the sp2 overlapping, and carbon hydrogen sigma bonds are formed by the sp2s overlapping. There are totally 1 2 3 carbon carbon sigma bonds, and 1 to 2 carbon sulfur sigma bonds, and 4 carbon hydrogen sigma bonds. This is about the formation of sigma bonds in the case of thiophene. Now we'll see the formation of pi bonds in the thiophene. After the sigma bond formation in thiophene, you can see this structure has come. So here the sigma bonds, carbon carbon sigma bonds, and carbon hydrogen sigma bonds, and also carbon sulfur sigma bond, and this is the lone pair of electron or non-bonding pair of electron is present over this. This is the bonding structure of the sigma bonding, showing it is showing sigma bond. So now I'll take that structure and just rewriting on the furan structure. For the formation of pi bonds in thiophene, if I just replace oxygen with sulfur as it is we have done in the sigma bond formation. Yes, here also you know that for carbon atom there is one unhybridized p orbital with the unpaired electron, totally for 4 carbons 4 orbitals, and the sulfur is containing an unhybridized p orbital with a pair of electrons. Okay, the carbon unhybridized p orbital and sulfur unhybridized p orbital, they all will involve in the pi bond formation. They show the sideways or lateral overlapping leading to the formation of pi bonds. So these all are forming a pi cloud over the plane or over and below the plane of the sigma bonds. Okay, so now this is the final structure of thiophene. Indeed, this is also the structure of thiophene. So you can see here, as I have shown the bonding structure pi bonds, I am writing the lone pair inside. So this lone pair, this pair of electron present in the unhybridized orbital, that is involving in the pi bonds, pi bonding, that is involving the delocalizations of electrons. So here these two, and these two, okay, the pi for 2 pi bonding electrons, 2 pi bonding pair of electrons, 4 pi bonding electrons and 1 this pair of electrons. So there is totally 6 delocalizing electrons, and here sulfur. So as I have shown a pi cloud which is involving 6 pi electrons, so 6 electrons. So that's why these electrons are involved in the ring. Here I have written, so that's why I'm just mentioning only the non-bonding pair of electrons. This is about the structure, that is molecular orbital structure of thiophene. Both furan and thiophene are similar. If you perfectly know the molecular orbital structure of furan, you can easily write the thiophene. That's why most of the time furan has been asked, thiophene still not has been asked many a times. Students, usually the questions will be formed like write the molecular orbital structure of thiophene and mention its aromaticity. So the question will be usually included the aromaticity. Hence now we'll discuss the aromaticity of thiophene. So as you all know, to any compound to show aromaticity, the compound must show or fulfill these 4 criteria that we already discussed in furan. So that's why whether these 4 criteria will be fulfilled by sulfur or not, we'll discuss now. The first criteria, as you know, the compound must be cyclic and involve the planar structure. So as you see here, the thiophene structure, it is completely cyclic. If you start the cycle with sulfur, it will end at the sulfur only. So it is cyclic in nature, and it is planar in nature because the all atoms in the bond forming, that is carbon and sulfur, are sp2 hybridized. As they are sp2 hybridized, the geometry of sp2 hybridized is trigonal planar. So that's why this is a planar in nature. So the first criteria is fulfilled. When it comes to the second criteria, it should have a delocalized electrons. So totally there are 4 pi electrons, 2 pi electron, 2 pi electrons, and these 2 pair of electrons involving the pi bonds, and all these 6 pi electrons will show delocalization, that is forming a resonance structures. We will discuss the resonance structure in detail when we discuss the reactivity of thiophene in the next class, when we discuss especially electrophilic substitution. We have to see the resonance structures of thiophene. This is nothing but conjugation, delocalization of electrons, that is leading to the resonance structure, that is nothing but conjugated system. So here also the thiophene fulfills this criteria. When it comes to the third criteria, so that is the compound should obey the Huckel's 4n plus 2 pi electron rule. The Huckel's rule states that a compound which is cyclic and planar with a completely conjugated system containing 4n plus 2 pi electrons, that will be aromatic. So if I put n here, the one single ring, n equals to 1, so then totally 4 into 1 plus 2, that is 6 pi electrons. 6 pi electrons. So according to Huckel's rule, the system containing 6 pi electrons, 10 pi electrons, 14 pi electrons, 18 pi electrons, etc., etc., they are aromatic in nature. They are aromatic in nature. Here also it has 6 pi electrons. So hence this Huckel's rule also been obeyed by the compound, hence it fulfills the third criteria also. When it comes to the last and final criteria, that is the compound must undergo electrophilic substitution reaction. For the electrophilic substitution reactions, we need at least one hydrogen, because the hydrogen only will be replaced by the upcoming electrophile. So in case of thiophene, as you see its molecular formula, that is C4H4S, there are 4 hydrogen atoms. These 4 hydrogens can be replaced by an electrophile, so hence it can be undergoing these electrophilic substitution reactions. So all these 4 criteria has been fulfilled by the thiophene structure, hence it is aromatic in nature. Therefore we have to write at the end, the thiophene is aromatic. Is aromatic. Yes, this is about the molecular orbital structure, and also we talked about the aromaticity of the thiophene. I hope you got all these things. Thank you. Thank you for watching my video. Please like and share with your friends and subscribe my channel, and also don't forget to hit the bell icon to get the updates of my upcoming videos. Thank you.